Okay, try and picture this. It's 1 minute after the end of the Cretaceous period, that's 65 million years ago, down near the Yucatan Peninsula, where the Gulf of Mexico is now. It's just sheer chaos.
Unimaginable, really.
Yeah, a huge asteroid, maybe 10 kilometers wide, has just hit. And in that first minute, this massive scar, like 100 kilometers across, rips open the Earth. Rock vaporized, trillions of tons of stuff blasted into the sky. And, the moon is just hanging up there, watching it all happen.
A world changed in an instant.
Exactly. So let's unpack that. We're doing a deep dive today into the science of meteorite impacts on Earth, and we're drawing heavily on this really comprehensive volume, CB954.pdf.
It's quite the resource.
It really is. And look, this isn't just about the dinosaurs, although obviously they're a big part of the story. We want to explore how these cosmic collisions have literally shaped our planet's geology, even steered the course of life. Think of this as a shortcut to understanding this really crucial geological process.
No surprises, too.
Right. And we should mention all this info comes from a scientific volume that's dedicated to the pioneers who first figured this stuff out.
It's actually amazing how recently we've really grasped how important impacts are. For the longest time, geologists kind of dismissed them. Minor events,
Geological side notes.
Pretty much. But that view's been totally flipped, thanks mainly to two big developments. Now we know these impacts are major players in shaping Earth's geology and its biology, too.
Okay, so it's like we suddenly realized these weren't just cosmic hiccups. What were those two game changers?
Well, first, just exploring our solar system. Sending spacecraft out there, the pictures came back showing craters everywhere. The moon, obviously, but also Mercury, Venus, Mars, even moons around Jupiter and Saturn. Asteroids.
So it's not just an Earth thing, it's universal almost.
Exactly. It showed us impacts are a fundamental process happening all over. And second, back here on Earth, we learned how to spot the evidence. Even for really old, eroded impacts, we found these unique effects in the rocks, shock metamorphic effects.
Shock metamorphic effects. Okay, that sounds intense. Like the rocks themselves remember the impact.
That's a great way to put it. It's like a fingerprint left by unbelievable pressure. See, when something hits Earth at, say, tens of kilometers per second, the shock waves generated are immense. We're talking pressures hundreds of times greater than anything from volcanoes or earthquakes. Hundreds of gigapascals versus just a few.
Wow.
And these intense, super brief pressures cause unique, permanent changes in minerals and rocks. We've found about 150 confirmed impact structures so far, but estimates suggest there are hundreds more hidden.
Hidden, like buried or just hard to recognize?
Both. Erosion wears them down, sediments bury them. But they range hugely in size. You've got relatively small ones like Barringer Meteor Crater in Arizona, about 1.2 kilometers wide, 50,000 years old. That was one of the first ones proven to be from an impact.
Where I've seen pictures of that one, just this big bowl in the desert.
Exactly. But then you have these ancient giants, over 200 kilometers across, maybe 2 billion years old.
200 kilometers. That's enormous. And seeing craters on other planets, like the moon, how does that connect back to Earth's story?
It gives us a planetary perspective. Basically, the more craters a surface has, the older it generally is. It's had more time to get hit. It's a way to estimate relative ages.
Like counting wrinkles, sort of?
Kinda, yeah.
Yeah.
Take Venus Magellan's radar, peered through the clouds and found loads of craters. Many were complex, with central peaks and collapsed rims. Then you look at Mars, you see things like the Ardjar Basin, huge, nearly 900 kilometers wide, super old. Maybe even a multi-ring basin.
Multi-ring, like ripples in a pond?
Something like that, yeah.
Yeah.
These huge features tell us about the really intense bombardment early in the solar system. They're like cosmic clocks, helping us date surfaces across different planets.
Okay, so impacts are common, they happen everywhere, and they leave these massive scars. But what makes the event itself so different from, say, a huge earthquake or a volcano?
It boils down to energy. The sheer amount of energy, how fast it's released, and how focused it is. Impacts release just astronomical energy. It all comes from the kinetic energy, the motion of the object hitting us. Remember, these things are moving incredibly fast, tens of kilometers a second. Even a relatively small one can hit with the force of many atomic bombs.
That's terrifying.
It is. And unlike an earthquake or eruption, where energy comes from inside the Earth over maybe minutes or hours, an impact dumps all its energy almost instantly, right at the surface at one point.
A massive sudden shock.
Precisely. Immediate catastrophic changes locally, but potentially affecting the atmosphere, the whole biosphere. And those shock waves we mentioned, They create pressures and temperatures far beyond normal geology.
So who are these cosmic vandals hitting us? Asteroids and comets, right?
Those are the main culprits, yes. Asteroids mostly rocky, from the belt between Mars and Jupiter. Comets more icy, from the outer solar system. But their orbits can get nudged, by planet's gravity.
And they end up heading our way.
Some do. They become near-Earth asteroids, or NEAs, and comets. Objects whose paths cross Earth's orbit. We know of hundreds of NEAs over 1 kilometer wide right now, big enough to cause global problems if they hit.
1 kilometer wide? Yeah, that sounds bad. It feels like we're in a bit of a shooting gallery.
Well, in a way, Earth gets hit constantly, but mostly by tiny stuff. About 100 tons of dust and small particles burn up in our atmosphere every day at shooting stars.
Okay, that's less scary.
Yeah, the big impacts are much rarer, but they happen. The source mentions some recent-ish reminders, like the Chicxulub event in Siberia, 1947. A small iron meteorite, maybe 3 meters across, broke up with a force of, 4 kilotons of TNT.
Still pretty powerful.
Oh, yeah. Then there was that object in 1972, about 10 meters wide, that just skimmed the atmosphere over the western U.S. energy of several atomic bombs. A near miss.
Wow.
And the big one, Tunguska, 1908. Siberia again, probably a 30 to 50 meter object. It exploded in the air in airbursts with maybe 15 megatons of force. Flattened 2,000 square kilometers of forest.
15 megatons, that's huge.
It is, and apparently it was a near miss for St. Petersburg. Imagine that over a city.
Yeah, sobering. Okay, so these things happen, but how do scientists study them? We haven't exactly seen a giant impact happen up close.
Right, direct observation of large impacts isn't possible. So our understanding comes from basically 3 things: theory and computer models, lab experiments creating tiny craters, and then detailed geological fieldwork at actual impact sites on Earth.
The detective work you mentioned.
Exactly. We need to distinguish between slower impacts, which just kind of punch in, and hypervelocity impacts. Those are the ones at cosmic speeds, creating the intense shock waves.
And those form craters differently.
Yeah, the hypervelocity ones typically go through 3 stages. First, contact and compression. The impact happens. Kinetic energy turns into shock waves in both the object and the ground. The projectile itself mostly melts or vaporizes.
Gone in a flash.
Pretty much. Second stage is excavation. Those shock waves blast rock outwards, digging a bowl-shaped transient crater. Material gets thrown out the ejecta. Then, third stage, modification. Gravity takes over. The transient crater is unstable, so it collapses. Walls slump inwards. Sometimes the floor rebounds upwards.
Ah, so that's how you get different shapes.
Right. Smaller impacts tend to stay as simple bowl shapes. But above a certain size, which depends on gravity and rock type, they become complex craters. They get that central uplift, a flatter floor, terraced rims from the slumping.
How big are we talking for that switch?
On Earth, it's roughly 2 to 4 kilometers diameter, depending on the rock. And these complex craters form fast. Even a giant one, like Vredefort in South Africa, hundreds of kilometers wide, probably formed in less than 15 minutes.
15 minutes? Incredible. You mentioned multi-ring basins earlier, too.
Yeah, those are the biggest structures.
Yeah.
Hundreds, even over 1,000 kilometers across. Multiple concentric rings. Think Mare Orientale on the Moon. They likely formed from enormous impacts, mostly early in the solar system. Identifying them definitively on Earth is tough because of erosion and burial.
But some candidates exist.
Oh yes, Chicxulub, the dinosaur killer, is one. Manicouagan in Canada, Papagai in Siberia, Vredefort, Sudbury. They're all potentially ancient multi-ring structures.
And the absolute key to confirming any of these sites, big or small, is finding those unique fingerprints, the shock effects in the rocks.
Exactly right. That's the smoking gun. Those shock waves create permanent changes unlike anything else in geology. The pressures, temperatures, how fast the strain happens, the time scale, it's all different.
So what are some examples? You mentioned shatter cones.
Shatter cones, yeah. They're distinctive fractures, cone-shaped with these striations radiating from the tip, kind of like a horsetail pattern. They form at relatively lower shock pressures, maybe 2 to 10 gigapascals, often found under the crater floor, especially in central uplifts. They're unique to impacts. Nothing else makes them.
Okay, a visual clue. What else?
Then there are high-pressure minerals. Finding minerals like coesite or schistosite, which are dense forms of quartz, silica, or even tiny diamonds in surface rocks, is strong evidence. These need immense pressure. Schistosite, in particular, has only ever been found naturally at impact sites, never in volcanic rocks, never deep in the Earth's mantle where pressure is high but different.
So finding schistosite is basically case closed.
Pretty much. It was finding coesite and schistosite at Barringer Crater that really cemented its impact origin. Then, maybe the most widely used microscopic evidence, planar deformation features, or PDFs, in quartz.
Yes, okay.
These are microscopic parallel sets of glassy lines inside quartz grains. They form at higher pressures, maybe 10 to 45 GPa. They're different from normal crystal fractures or features formed by tectonic stress. Crucially, they form along specific directions within the quartz crystal structure.
Like along the grain.
Sort of, but very specific crystallographic planes. And different sets of orientations tell you about the peak pressures the rock experienced. Finding quartz grains full of these PDFs, especially multiple sets, is considered definitive proof of impact. They were absolutely critical for proving the Chicxulub impact at the KT boundary.
Tiny features telling a huge story.
Absolutely. There's also shock isotropization minerals like quartz or feldspar turning into glass without actually melting, and selective melting where the heat after the shock passes is enough to melt some minerals but not others. Finding Tellurite, which is pure silica glass formed from quartz melting above 1700 degrees C, is another strong sign. You basically only find it in impact rocks and, weirdly, in fulgurites where lightning hits sand.
Wow. So all this intense shock and heat creates entirely new types of rock, impactorites.
Precisely. Impactite is the general term for any rock formed or modified by an impact. That includes the shock target rocks themselves, various kinds of breccias, which are just rocks made of broken fragments cemented together, and importantly, impact melts.
Okay, breccias and melts.
Yeah, they get classified based on where you find them, under the crater, inside it, on the rim, or thrown far away. That's distal ejecta. Also based on what they're made of. Below the crater, you might find shocked rocks still in place, or breccias filling cracks, sometimes with melted rock matrix called pseudotactylite, likely from friction.
And inside the crater?
That gets filled with debris after the excavation stops. You get breccias made purely of rock fragments, lithic breccias, or mixtures of rock fragments and glassy melt fragments called swivites, or impact melt breccias, where fragments are swimming in a matrix that was completely molten.
And the melt itself?
Impact melts form from rock melted by the shock heating. The amount of melt depends on the impact size. You find layers or pools of it within and around larger craters. They often show signs of extreme temperatures, things like zircon crystals, which normally survive a lot, being melted or decomposed. That Sudbury structure in Canada, the main geological unit there, the Sudbury Igneous Complex, is thought by many to be a huge sheet of impact melt.
How do you know it's impact melt and not just, say, volcanic rock?
Good question. Several clues. It usually doesn't look like typical volcanic rocks from the region. It contains fragments, zeoliths of the target rocks it melted, sometimes showing shock features themselves, and chemically it might have anomalies, like higher levels of elements like iridium, which are rare in Earth crust but common in meteorites. Or specific isotope ratios, like osmium isotopes, can point to an extraterrestrial component mixed in. Dating the melt also helps pin down the impact time.
So it's a whole package of evidence, physical structure, shocked rocks, impactites, chemistry. It sounds like we're still finding these things too.
Oh, absolutely. Identifying new impact structures is still ongoing. It helps us understand the whole process better, figure out how often impacts of different sizes happen, and lots more. People find them through field work, looking at geophysics data, satellite images, sometimes drilling. But confirmation always needs those shock effects or a chemical signature from the impactor.
And the significance goes way beyond just geology, right?
Yeah.
Extinctions.
Definitely. The link between Chicxulub and the KT extinction, the end of the dinosaurs, is rock solid now. But there's other fascinating stuff too, like the source talks about carbon chemistry. Finding nanodiamonds formed in the impact plume, or fullerenes, those buckyball carbon molecules in ejecta from the KT impact in Sudbury. It raises questions about where the carbon comes from and maybe even about prebiotic chemistry, the steps leading to life.
Wow, impacts and the origin of life.
Potentially linked, yeah. Also, after the impact, the heat can drive hydrothermal systems, hot water circulating through the fractured rock. This can sometimes create ore deposits. And the lakes that often form in craters afterwards can preserve amazing sediment records of the environment recovering.
So craters become like little time capsules.
Exactly. And looking way back to the early Earth, impacts were likely even more frequent and larger. They probably played a huge role in forming the early atmosphere, delivering water and organic compounds, and just generally causing massive shakeups in Earth's very early history.
It really is mind-blowing. The sheer power, the time scale, thinking about these cosmic collisions shaping everything from landscapes to life itself, and how we piece it together from these subtle clues in the rocks. Okay, as we wrap up this deep dive, what's a final thought you want to leave our listeners mulling over?
Well, considering we're still finding these huge scars on Earth, and we know there are plenty of near-Earth objects still out there, it makes you wonder, doesn't it? What other secrets are locked away in these impact structures waiting for us to find them? And what does this constant potential for collision really tell us about our place in the solar system? It's a dynamic place and sometimes a pretty dangerous one.